Okay. So a spring or an elastic force is one that changes. So when we have a spring, and most of us have a spring in our ballpoint pens. See if I can unscrew this one. It's a little spring that's inside your pen. And you realize that you can click your pen up and down, right? So when I click my pen down, I'm compressing the spring. But if I try to compress the spring, it gets harder. It tends to want to bend more than it wants to compress, right? It gets harder and harder to squish it closer and closer. Likewise, if I have it spread out, it can stretch out a little bit this way, but if I go too far, what happens? I lose my stretchiness, yes? Like if I pull this all the way apart, now I've lost the ability to do a click on my pen because the spring will not stretch, nor will it go back to its original shape. So when we talk about elastic forces, an elastic force occurs anytime you have an object that can return to its original shape. So for example, a racquetball, a tennis ball, golf balls, all of those will change their shape when they come into contact with something else. For example, with basketball, when you dribble the basketball on the floor, to the naked eye, as we say, you don't really see the basketball squish on the floor. But if we watched it in slow motion, you would see the bottom part of the ball flatten out a little bit, and then it would spring back to its normal shape. Tennis balls are a lot more obvious when you see them hitting a racket. So let's look at that for just a second. We'll talk about some of these forces. So when you, that guy, slow-mo video of golf ball compression, just to pick one. So if you've never seen this, this is being shot at 70,000 frames per second. And that's a golf ball hitting a metal plate. It's very upsetting because that doesn't look so ball-like right at the moment. So it's going to continue to sort of wiggle and wiggle. But remember, 70,000 pictures per second. So we're seeing this very, very, very slow motion. I'll let this one go too because it's another short one. But this is one of the things they test is the golf ball and how easily it compresses and then how easily it goes back to its original position. So this is what they do at one of the test facilities for Titleist. He's the guy that's the head of this department. Boy, I wish I had that swing. So they're going to shoot this with a high-speed camera at their test facility for Titleist. So there's kind of a slightly slow-mo version. And here's the different ball speeds coming off the tee. So this is your not pro golfers. And that's still a pretty good golfer. If you can get the ball at 120 miles an hour, that's a pretty good golf swing. But what would they want to see? Do they want the golf ball to perform the same way regardless of club head speed? Or do they want it to have better performance as it goes faster? It kind of depends on what you're looking for, right? As a person that plays golf and is not good at golf, I want a golf ball that is sort of soft. And what we mean by that is if I don't hit it in the sweet spot, I can still get good carry and behavior from the golf ball. So it squishes a little bit more than the one the pro uses. The pro is good enough to put the ball exactly where he wants or she wants. And so she's going to be looking for a performance that's a higher level than mine. So that if they want to hit it at a little bit of a slice to dog leg one way or the other, then they can do that. So that's one of those things that they have to work with. But you can see that the higher speeds, you weren't seeing a true compression, but you were seeing a pretty decent amount of squish, right? Now, here's what you don't see because you don't have the face on camera very well. The golf club head also compresses a little bit, but it doesn't compress nearly as much because what is it made out of? Drivers tend to have metal or aluminum carbon fiber, some sort of composite on the front that's a little bit sturdier than the skin of the golf ball. So it does not give as much. Just like if you were to, and we don't have the equipment in here to measure it, but if you were to press against this wall, if I press against this wall, the wall is going to compress a little bit. And by a little bit, I mean micrometers, millionths of a meter. So like take a meter stick, I say, take a meter stick, like there's one sitting here because there usually is. So if we're to take a meter stick and you were to take each one of these little guys, you know, your centimeters, and divide that by 1,000, that would be how much it compresses. If you can imagine taking one of these cute little guys, millimeter divided by 1,000, that's what we're talking about. So yeah. Does it move? Yes, I've seen that done in lab. Yeah, good job. All right, so some elastic forces that are not, that are only one way are rubber bands, because rubber bands only do one kind of stretch. They stretch, right? But if you let them go, they'll snap back. But if you kind of smush them together, you don't really get a push back to the original size. You know what I mean? So rubber bands are a form of elastic, but they only work in one direction, sort of. So the force is not gonna change, and objects, this occurs with objects that return to their original shape. So we're gonna do a lab, and I'm actually gonna, you may have seen that I had stations set up. I am gonna do a physical lab here too, and we're gonna rotate through so that you can put your hands on the equipment, but we'll have to do that with small groups, you know, so that we don't stay within 6 feet for more than 15 minutes. One of those things. Okay, so I've just removed to the original shape, and the thing we're gonna talk about is horizontal springs and vertical springs. That's the two that we're going to focus on with spring forces. And the equations we're going to deal with here, equations we'll be using are our kinematic equations, our big three, and our force due to a spring is negative K delta X, where K is called the spring constant. It measures stiffness of the spring. Let's scroll it up just a little bit. Okay, so just to get some terminology for ourselves today. And some of these words you've probably already heard, and some of them you may not have. Never know from year to year. So equilibrium position for a spring is a little bit different than it is for a regular object. The equilibrium position for a spring is its unstretched length. So when I took the spring out of my pen, it had a length, a natural length. That natural length, the middle of it, the exact middle, so it's not stretched out or stretched in, would be considered the equilibrium position. So exactly in the middle of the unstretched amount would be our zero, okay? You can put your zero, now remember, because this is physics, you can put your zero anywhere you want to. So if Chase wants to put his zero here, that's fine. And if Michaela wants to put it here, that's fine. And if Jacob puts it here, that's fine. But you'll get different numbers for your answer, but you may have said the exact same thing. Just like if I call the ground height 0, but Gabriella decides the top of her desk is going to be height 0, we will both see a displacement that's the same if I move an object to the ceiling. But we would record different numbers for it. So in general, we put our equilibrium position in the middle of our most compressed and our least compressed, which makes it at the unstretched length, if that makes sense. So what would the A stand for? What do you suppose the A would stand for? Yeah. Say again? The most and the least stretch, yes. And what word goes with the most and least on something like this? Well, you may not know this, but it's called amplitude. It is the maximum amount of stretch. For a particular spring. Maximum amount of stretch, it's called amplitude. So what does the spring constant do? So we got amplitude is the furthest out I can go this way, or the furthest out I can go that way. On this side, it would be the most compressed, right? On this side, it would be the most stretched. So if Autumn was to grab this mass and pull it past A, her spring would not spring anymore. It's not capable of going that far out. So there is sort of a, I can't go any further place. Just like when I take a spring and squish it, I can only squish the pieces so close together, right? Like if I have a slinky, there's only so tightly I can mash it together. Physically, there's properties with that. So this amplitude is going to be our maximum amount of stretch possible. Sorry, let me get that over just a tinge. Easy way. And scroll that up. And what is K going to measure? Well, K measures the stiffness. So you may know that the school buses have shock absorbers. You may not believe that they have shock absorbers. I understand that, because if you've ever ridden in a school bus, especially if you're in the back over the wheels, it does not feel like there are any shock absorbers in this vehicle, right? So, but there are shock absorbers, and the shock absorbers on the bus are actually springs. They're about this big around. They're huge. They're thick. So then why do not stop? How come they don't work, right? Well, partly because they're so big and thick and squatty this way that they don't have a lot of room to move. And not having a lot of room to move is good because you're trying to keep the bus from really bouncing up and down. But because they are so tightly packed, you don't get all of that bouncy road effect taken care of. But you do get a lot of it. So I guess my thought to you would be, if you ride a school bus, it's a lot better than it could be. But I know it's not nearly where you'd like it to be, especially if you're on the back or if you're somebody that's car sick. So a spring constant for a school bus might be 10,000 newtons per meter. But the one that's in my pen might be 1/10 of a newton per meter. So the K value tells you how stiff or stretchy your spring is. So large K values, require, bless you, a lot of force to stretch or compress. So large K values might be something like K is 1,000 newtons per meter, or K is 22,000 newtons per meter. Those would be large K values. So what does that tell me? Well, to put it in English units, because I know most of us are better with the British imperial system that we live under as far as our unit measures, a K value of 1,000 newtons per meter would be equivalent, about equivalent to 2,000 pounds per meter. In other words, to get your spring to stretch 1 meter, here's your 1 meter picture, right? To get your spring to stretch 1 meter, that first K value, you would have to apply about 2,000 pounds worth of force. That's a lot of force. That's like smart car weight kind of force. So that would be a very stiff spring. So what happens to a very stiff spring? It only stretches little tiny amounts, right? If I take a slinky, what's a slinky got for a K value? Since we've all probably seen a slinky. Really, really low. Yep. So for something like a weak spring, small K values easily stretch or compress. So K might be 0.01 newtons per meter, or K might be 100 newtons per meter. The second one, the 100 newtons per meter, just to kind of put this in perspective, if the top ones require you to lift a Volkswagen Bug, like pick it up, that's the amount of force you need. Then the bottom ones use stuff like, hey, come on in. Any questions? Okay. So the small ones would be, this would be about the amount of weight in an apple. So if you pulled it with the weight of an apple, it would stretch a whole meter. You can kind of imagine I'm holding it. Apples don't feel like they weigh very much, do they? Some of them do. Those Honeycrisps, some of the Honeycrisps get to be like grapefruit size. But most of your regular apples, you pick it up, it has a weight, but it's not something that you kind of consider as being a problem. But that amount of weight or that amount of force would cause it to stretch a whole meter. So these are things like your ballpoint pen, clicky spring, okay? This would be more like if you guys have ever done fishing, you know, when they hang a fish up to weigh it on a spring scale, that's what that's called. The spring values on there are usually between 100 and 500. Depends on what kind of fish you're playing with there. Because some fish, you fight them like they're 10-pound fish, and then you get it, it's like, oh, it's a trout. It's 2 pounds. You fight like mad, trout do. But then other fish are kind of like, that requires effort. Just drag me in. Okay. They'll fight for a little while and then they give up. And then catfish are really bad because once you get them out of the water, they moan at you. I don't know if you realize that. If you've never caught catfish are dumb, just to be honest. I caught one with no bait one time. I was just fishing to pass time and I ran out of bait, so I'm just casting a bear hook out there. Caught a catfish, probably about 1.5 pounds. It was a baby, but still, that's stupid, right? Like, got it up on the bank, and it's just moaning like it was awful. That's like the worst sound ever. Some of you know what I'm talking about. If you've never caught catfish live, you don't know, but they really do sound terrible. You feel terribly guilty for the noise they're making.
I've never heard them moan. They just flop everywhere.
Well, they do flop everywhere, but this one just laid on the bank, and it, the sound you imagine a dying cow to make is kind of the sound the catfish was making. So miserable. So, okay. So what are we going to deal with on these guys? Where would the most potential energy be in a horizontal spring? Where would you have the most potential energy? Either at A or negative A. Completely compressed or completely stretched. That would be where you have the maximum potential energy. The energy is stored in the spring. So gravitational potential energy depending on your height off the ground, is stored in the gravitational field. But a spring is not gravitational potential, it's elastic spring. So the elastic energy is stored in the spring itself because of the molecules and their placement is what it amounts to. So you have most potential here and here. So what does that mean about your kinetic? When would the spring be moving the fastest? When would be the biggest kinetic energy? At the equilibrium position, exactly halfway in between. So I'm going to pull up a simulator real quick. Yep, real quick. It's okay. This is a safe space. You're welcome to be wrong in here all day. I'm not going to make fun of you for it. I'll leave your friends to do that for you. Because one of my favorite lyrics of a song is "True friends stab you in the front."
What song is that from?
Let's see. The song's called "True Friends" by Bring Me the Horizon. They also start a song with "Do You Want to Start a Cult with Me?" which I think is a great opening line for a song. That's another one of my favorite songs by them. A cult, yeah. Start a cult.
You could make your own call.
Well, back when Mr. Reed was here, he accused all my students of being a cult because they were always together trying to figure out the homework. But anyway, okay, so this, as soon as I hang that weight on there, this would be the stretched length. This would be what we call equilibrium. It's called equilibrium on a vertical spring because the spring is going to stretch down a little bit. It just has to. There's some weight pulling it down. So in this scenario, we would have weight pulling down. Weight is our force down, and spring force would be up. And at this moment, they would be balanced. If I hang more mass on there, what's going to happen? Oh, off of there. They should have hooks on the bottom, I think. Okay, so it stretches further. But it doesn't let me. Okay, I'm gonna have to get the other simulator out. So get our stretched length. 250 grams stretches a lot. So where we would put our zero would be down here right at the bottom of my measuring device. So when I stretch it down, now I'm at an amplitude. It's going to go down some number of centimeters. And then when it goes up, it's going to pass the balance point and overshoot it to some amount. Now, I've got friction on right now. Not friction, but damping on. And I can pull this spring. See how that spring gets fatter? If I make it a larger K. The larger K does not stretch as much as the small K does. Get out of the way. Okay. So let's get something that's a little bit easier to see. Let's let that thing do its thing. We put resting position. This is our equilibrium. Then I'm going to stretch it down and let it go. Oops, too far. Come back. So if I stretch it a little bit, it comes back up. Why does it not go all the way up and down? Why is it not going up and down and up and down and up and down? Ah, it's a thing called damping. I don't know if you're familiar with that. Let's put the resting position up here. So, medium spring stiffness, pull it down, and it's hypnotic. You may lose track of what we're doing because you now will buy me a puppy. Oh, wait. Darn. Okay, so if you notice, and I know it's hard to tell because it's moving pretty fast, but however far it stretches up, so we've got, this would be our amplitude, okay? And then if you watch when it goes back up to the other side, when it gets to its maximum compression, you'll notice the distance is once again that same height. So amplitude up, amplitude down, same thing. Why does it keep bouncing back and forth? Well, if you do not have any restrictive forces like air resistance, friction, what's going to happen? Well, there's no, what's the only force that acts? Well, the only force down that acts is gravity. The only force up that acts is the spring force. But the spring force does not stay the same number. So when the pendulum bob, or in this case, the 100-gram mass goes to the bottom, the spring force is getting larger and larger and larger and larger, but gravity is staying the same. The weight stays the same. So now we've got a big force up, smaller force down. So what do? Accelerate up, which means if you're moving down, but you accelerate up, you slow down. When velocity and acceleration are in different directions, you slow down. But then when it hits that bottommost point, now we've got a huge force up, small force down. Now we start to accelerate up. What happens when I reach equilibrium? What's true of my forces at that moment in time? Say that again. Not at the equilibrium position. As soon as you go past equilibrium, the forces will be different sizes. So what happens at equilibrium? The forces are the exact same size. And since the forces are the exact same size, at that moment we have balanced forces, right? What does it mean to have balanced forces? What do Newton's laws say to you when you get the forces are balanced? You keep moving at the same speed in the same direction. So our mass on a spring can't stop because it was moving. So when it gets to equilibrium, it keeps moving in the direction it was moving. But as soon as it passes equilibrium, what happens? Now the gravitational force points down and the spring is now getting compressed. So now the spring wants to push down as well. It wants to go back to its regular length. So let's see if we can show you that so that you can kind of see what's happening. And I think, let's see if this is the one I want. Yes. Yes.
So you said if it's vertical, like hanging down, when you put the weight on it, it's the center, like it's the equilibrium. What happens if you're like on a table?
The equilibrium position will still be in the middle, and we'll show you those in just a second. It'll just be sliding this way.
Yeah.
So you don't have gravity as a force anymore.
So it would just be.
It would just be the spring force, right or left. So you apply a force at the beginning to either compress it or stretch it. And then after that on a horizontal, the only force you have left is the spring force, which is changing size as you move. Yep, good question. We'll come back to some of those. So let's pull this down a little bit. So pull it down a little bit, and I want you to see the acceleration arrows. If it will show it. Too far. Look what happens to the acceleration arrow. You see it? Up, down, up, down, up, down. Slow motion. See how it gets bigger? And right when we get to equilibrium, the acceleration arrow goes away because we have no net force. Our forces are balanced. But as soon as it slides past that position, now it points in the other direction. So if we were to stop this, make this a little bit weaker spring, stop that, pull this guy off, this guy on. This will make it a little bit more obvious. So you see what's happening? Let's take off, this shows you your force and acceleration. So let's change that to velocity. Stop, turn around. Fast, 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 fast. Oh, slow down, slow down, slow. Stop, turn around. So where do we have the most? Where is our biggest velocity arrow? Moving fastest at equilibrium. But as soon as I go past equilibrium and my spring starts to compress, now my velocity starts to go down because the spring is pushing down, but the object's still trying to move up. Kind of got a feel for this now? Okay. So I'm going to stop there for today. We got just a few minutes before we go into connect and impact time. So, so the link to join Pivot is here. If you want to fix the quiz questions, you're welcome to do that. And you have some book questions about kinetic energy and potential energy. So all of those good to go. That's all for today, folks. Thanks for showing up. I appreciate it. If you didn't hear me say this when we first came in, number 3 and number 10 had errors on the quiz. So if you want to go back and redo 3 and 10, you're welcome to do that on the quiz. And just make sure your name's on there twice. So you only have to do those 2. I'll grade those separate. Okay, then I'll go change that. I don't remember setting it to do that, but I believe you. Well, those AP problems coming for you, Nathan.
We're gonna have to do them.
Okay. Yeah, I figured. Settings. Okay. It should be fixed now. See if you can get in. So you guys can stay for Connect and Impact. I'm going to go help Nathan for a few minutes and I'll be back.
This is what we're doing. Yeah. Like there's the forces. So I think
You did fine on the first one.
I did fine on that.
You did fine on this.
Yeah.
Except for that one.
Yeah.
Okay, so this one's bad, right?
Yeah, like it looks so innocent.
Yeah, you grab a piece of tape and it's tape all over it. Not like Sean said, it's not hard. But it's gonna unlock the tape without switching. One of them there is this, so drawbacks are showing all forces acting on the cylinder after the release.
Oh, I didn't label.
Yeah, but you got it. So it's from the center mass you have force gravity this way. And out here on this side, we would have force, yeah. And really, this is it's not an applied force, it's closer to a tension force just because of what it's doing. But yeah, T would be good because that would be purposely way. So, in terms of G, find the downward acceleration of the center of the cylinder as it unrolls from that. What forces do we have? You know it's going to accelerate.
That we do.
So this is gonna be mg, this would be negative ma. We call this down, we gotta call it down. And then you have force tape.
Okay, I agree.
So then what's your sum of your force?
There's one force
There is one force,
and it's R out.
so this would be whatever that tape force is, times our radius is 1/2 mr squared. No. But the problem is, let me make sure. I want to figure that something. Okay, so they did not say anything about the expected change in rate. Okay, if they did, this would be, what happens to your radius if you go pretty smaller? The radius gets smaller, which means that there would be an R, the dr piece would be negative in the context of the question. And so you would have to consider that in terms of your integral, that the R was not, so you'd be going from near the R. I don't think they expected that in this question, just compared. Yeah, that's what we make this. Okay, off you go if you got stuff to do.
I agree with you.
Okay. So then we're here,
Yes. I'm
and without slipping, so we got. There's without slipping, there was this,
Yes.
which then, this R gets one of those, this one gets the other one, and we'll get 1/2. Yep. Now, but if they asked us to do this, that's not easy. So then the question becomes, is that really all we had to do? And I'm pretty sure for that part that is. Yeah. Let me see if anybody's still left. Yep. Hi, Jackson. If you need something, holler at me. Yeah.
We talked about like identifying the name on it first.
Yeah. Is it still not showing up?
Yeah. It's
Okay,
just-
okay. Okay, I'll fix it. I put it in, that's why I gave it back to you, but
Okay.
that does not mean it keeps it sometimes.
Yeah, without flipping, so it's left and down. Final answer.
So,
Left and down.
okay, what year was this? What year was the question? 88,
76.
76. Hey, I was 5 years old. Yep, so tension or force tape or whatever is 1/2 ma. So acceleration is 2/3 gravity. As there are no horizontal forces, the cylinder moves straight down.
It just goes against everything I would think.
What does the tape do? Let me put this grade in for him too while I'm up here. What does the tape actually do? What does that force tape do?
It rotates.
Does it push to the right or left?
No.
No, it grabs the side and it makes it unravel, unroll.
No.
It provides torque. I know, that's why that asked that question, because that's the most common mistake we see on that.
It feels like it should rotate though.
But that's where you got to trust your force diagram. Does your force diagram have any horizontal forces? No, so trust it. That's the whole point of that piece. Okay. Dylan, that was the
Yeah.
Sankey diagrams, right?
Yeah.
Okay. Have a good day, my friend.
I'll try.
Okay. And any of the rest of you, if you're working on stuff, please feel free to ask questions, because Jackson's going to stay over here and I'm gonna wander around the room from time to time, so you're welcome to ask. Is that a stretch or an ask? It's both.
Well, yes,
Yes.
but, okay, I just wanna know if I'm missing
Uh-huh.
So you have, you're given mass and you're given kinetic energy, basically. So it's four,
Way harder than ask.
well, no, this is just my work for the entire quiz.
Okay.
But, if it's 4 newtons over 12 meters, so it'll be 4 times 12 is the number of joules. That's 48, and then that would be equal to the kinetic
Yep.
equation.
Yep.
And then the mass of 1, so then it just becomes 48 equals 1 velocity squared. It's 24.
No. Divide by 2 on both sides? Algebra. It gets us every time. Yeah. That darn algebra. Not our friend.
Math teachers about what fractions are, friends over here.
Yeah. Fractions, I really feel more comfortable with doing fractions than I do, decimals.
Yeah.
Because mathematically, a lot of times the problem is written so stuff will cancel out. But I also understand that if you did, y'all have grown up with calculators. We were not allowed to use calculators for anything. Like I had to learn how to do square roots by hand. Not the 4 decimal places. And basically it's just a long division. Like it's not a big deal. It's just a different kind of long division. We had to do logarithms without calculators and stuff like that. So in my head, I can generally think the math faster than I can
I
calculate my
gotta use
calculator.
math work.
But if you haven't had to do that, then you're not as quick on the multiplying, dividing, and all that kind of stuff. So then it feels more comfortable to not do it. Did that fix that?
Yes.
Some days we have troubles. Yeah, my class is the one you get your quiz back and it's like, 5 times 5 is 10. No, it's not. 5 times 5 is 25. Where 5 cubed is 25, and it's not. And 2 times 3 is 5, always. So you're so busy worrying about the physics that you like brain fart on the simple arithmetic. It's kind of a common thing in here. Physics gets you in every which way you're working. You got to finish yet?
No, I'm working on art.
Fun.
Yeah.
And I'm going to grade for a little bit unless somebody needs me. Bless you. I had a sneezing fit last night in my house. I have no idea why. Like 30 minutes worth of almost constant sneezing. Very frustrating. So is the World Series going to end tonight or not? You think? I loved how the Dodgers were making excuses for why they might lose this year before they ever got going. It's hard to get up for the starting games. We've played so many postseason games, they just don't matter. Yeah, I don't buy that for 1 second. Maybe if you were the Yankees in 29, that'd be different, but. Okay, so Dylan, I put it in again, so hopefully it'll show that the next time you look.
Okay.
And Juliet, I told you I put your grades in, right?
Yeah.
Okay. Okay, let's see. This. Okay, so only 13 of you have registered for the AP test. It's on AP Classroom. You've got to get that done, like now, at some point today. Try to get that done, please.
Do you know who it is?
Yep, Juliet, Lauren, Dominic, Tyler, Christian, Ruben, Autumn, Krupa, Jacob, Connor, Chase, and Dylan. So make sure you get that done. It's on the page under course information, unlike AP test registration with the code and everything. It's always my kids that are running behind because since I handle it, I tend to not remember as frequently as I probably ought to.
So wait, what do I need to do for that then?
I'll show you. You have an AP Classroom account already, Jackson?
I don't know.
Okay. Well, then if you don't, you'll go to just Google search AP Classroom and you'll set up an account because that's how they'll send your AP scores. I'll show you where it is in the notebook. So I turned off the projector. Okay, so if you go up to course documents, you see where it says AP test information.
Yeah.
There's the information, except that they changed this to 95 after school started. And then the code for it is AP Classroom. So you go to AP Classroom and there's our course code and there's a video of how to do it.
Okay. Thank you.
Yep, thank you. I appreciate it. Okay, now where was I? I'm trying to get all the kids that don't go to our school that take tests here figured out too. Like homeschoolers and stuff, if we're offering the test, they can come here and take it with us. Because a lot of the other county schools won't let them. And I get that, but we get to keep their money. The $9 that we get rebated back to help with our programs, we keep that. So it's a thing. That and what does one kid matter really?
McDonald's knows off of that.
It's like $2 menu meals. Okay. Good book. And then second period.
Would it be better to put my own email or the school email address?
It's whichever one you want to use that you're going to check because they'll send your scores to whatever email account you pick. So just make sure you remember how to log in and all that stuff with that email. So I get people do both. Some use their personal account and some people use their school account. Either way is fine. But if you don't remember login info, I can't get that for you. You'll have to call AP, and we try not to do that if we can help it. They're not real good at answering questions. Also, next week, there's going to be a full day of pictures for school pictures, makeup pictures for faculty, makeup pictures for staff, makeup pictures for students. And they'll make announcements as they go. So next week is the makeup picture day. They didn't say which day. They just said it's next week. So it's usually Tuesday or Wednesday. And distance learners, if you want to come in that same day from 3:30 to 6:30, that's when they're going to do y'all's class picture for the yearbook.
Do you know if we're getting IDs this year?
I don't know. We talked about it and I never knew what they decided. I'm kind of okay with whichever they choose. Either we check them or we don't. When I first started working here, everybody had to have their badge where we could see it. And that's because we'd had problems with kids from other schools that were out of school for whatever reason, coming over here and wanting to eat lunch with their friends and or bringing stuff in. And really, you don't know if somebody isn't marked as one of yours, you don't know who you just let in the building. Because I love you guys, but you're really sweet. Like somebody's knocking on the door and you're like, oh, come on in. We're like, no, that could be bad. But yeah. When we've done all those drills with Code Reds, that's what we've noticed about our students and faculty. The faculty are more like where do you need to be? But the students are like, yeah, come on in. The office is down there, you know, and help you find wherever you're going. And that's great. Except if it's a bad person. So things to keep in mind. Maybe not so loving and gentle and helpful.
Like, what are you supposed to do? Just walk past and not?
Well, you're supposed to tell them that they are supposed to go to the front office and where that is to check in. And then you let somebody know. If you let them in the building, that's fine, but let somebody know. If it's an adult, let somebody know.
Yeah, there's like this big tall guy with a gun in the building.
Yeah. He looked like he hadn't bathed in 3 days and was kind of talking to himself, but he seemed nice.
Yeah.
Like,
You got a long coat on, a nice brown fedora.
So funny.
He didn't say much to me. He just grunted. But
Yeah.
I
He
think
said
he likes
thank you
me.
at least.
Yeah.
He was pacing outside.
I wonder why.
It's so funny. Well, you know, a few years back, we did a drill, you know, how we have the drill week. And our drill here was that it was an angry parent coming and looking for a particular teacher. And so the guy, it was a cop that was one of our SROs. I don't know if y'all remember Officer Martin. It's been a while, so I don't think you remember him. Big, tall, black man, just really stacked. Very nice guy. Loved him. But it was one of his friends, and he had on flannel, and it was like September. No, it would have been March then, right? The spring one. It's probably March. Had on a like a flannel vest and a hat, and was talking to himself, and was driving his car crazy in the parking lot. And people let him in down there by the gym, and he kept talking to himself, and then he started yelling, and we started yelling. That's when our students finally responded to it. But it was like, yeah, I guess he's just a little off today. He was in the building like 3 minutes before anybody knew that we should probably be warned about that. But, and they showed us videotape of what he was doing in the parking lot. We're like, why is nobody reporting this? But, you know,
Have you seen the kids that go to school?
yeah, I have seen you drive.
Me?
Not you drive personally.
I've seen you drive.
But I've seen you drive. One of the first years we were open, you know how they used to let the managers for the football team drive the Gator.
Really? I don't?
I-
You drove by me how many times?
I don't think they do now. Dylan, do they? Do they let the managers still drive the Gator for football?
I haven't seen it. I mean,
Okay.
They don't really, I mean, there's no really point.
Yeah, and so used to they would
Oh, wait, yeah, they do actually.
they'd let the managers